Welcome to the channel. I'm Carlos Ortega, and I'm excited to explore the amazing worlds of physics and chemistry with you.
You set your oven to 350 degrees to bake a batch of chocolate chip cookies. If you encountered 350 of almost anything else, miles per hour or pounds of pressure, it would violently destroy whatever it touched. Yet your cookies emerge perfectly golden brown. That number, 350, is a localized dialect. When we step outside and say the air feels hot or cold, we are describing a personal biological sensation. Without a standardized scientific context, those words have no objective meaning. To understand what is actually happening inside that oven, we treat temperature as a microscopic speedometer, a measurement of the average kinetic energy of the atoms and molecules bouncing around inside a system. Greater kinetic energy means those invisible particles move faster. The macroscopic sensation you feel as heat on your skin is the physical impact of countless high-speed, microscopic molecules colliding with you. This presents a massive engineering problem. Scientists cannot simply look at a microscopic molecule with the naked eye and clock its speed. Because we cannot directly observe this kinetic energy, we had to invent physical translators, tools that convert the invisible velocity of atoms into a visible, quantifiable language we can actually read. The most common tool for this translation relies on a physical workaround known as thermal expansion. As particles gain kinetic energy, they collide and push away from one another. The substance expands. Traditional thermometers trap this liquid inside a narrow tube. The thermal expansion is forced upward, allowing the column's height to act as a proxy for kinetic energy. But a rising column of liquid is useless without a scale to read it against. In 1742, Anders Celsius devised a way to standardize this expansion into a universally measurable language. Celsius anchored his scale to water. 0 point exactly where water freezes, and 100 exactly where it boils, divided into 100 equal steps. Around the same time, physicist Daniel Gabriel Fahrenheit was promoting his own competing measurement system, choosing a different physical anchor for his 0 point. Instead of pure water, Fahrenheit used a specific mixture of water, ice, and salt. Because this brine freezes at a lower point than pure water, his entire numerical scale is offset from the Celsius system. This explains the oven paradox. 350 degrees Fahrenheit is simply a different mathematical dialect. In the Celsius dialect, that same level of molecular speed translates to roughly 175 degrees. The actual kinetic energy is identical. We are just using different numbers to describe it. However, both Celsius and Fahrenheit are relative, arbitrary scales, based solely on how specific local water mixtures behave on Earth. In 1848, William Thomson, Lord Kelvin, recognized the need for a truly objective, universal scale for thermodynamics, free from the quirks of any arbitrary substance. Instead of anchoring his scale to freezing water, Kelvin looked downward. He based his 0 point on the total, absolute cessation of all kinetic energy. This theoretical minimum limit of the universe is called absolute zero, or 0 Kelvin. This antique thermometer shows how different physical mechanisms, like a spiral-shaped metal coil or liquid expansion, can be calibrated to multiple temperature languages simultaneously. Each is a technological translation of the same physical energy. Temperature is the average kinetic energy of atoms, translated into numerical values we comprehend and compare. But measuring this molecular speedometer is only half the story of thermodynamics. If heat is the kinetic energy of microscopic motion, we still have to explain how that energy physically travels. How does the frantic molecular speed of a burning campfire successfully cross empty space to warm up the cold atoms in your hand? Answering how we measure heat leads to the next crucial question. To understand the thermal universe, we must trace the 3 paths energy uses to travel, first through conduction, then through convection, and finally radiation.